Hello everyone, I will introduce the portable electronic nose project designed by our team. The part 1 is introduction. Our team's electronic nose design aims to solve the practical problem of traditional electronic nose. Although traditional electronic nose devices perform well in fields such as medicine diagnosis, they are generally large, heavy, and inconvenient. to solve those problems, we propose a portable electronic nose to provide the user with real-time gas detection data. And then it's part 2, background traditional electronic nose. The traditional electronic nose simulates the human sense of smell and enable gas recognition through gas acquisition sensors array and data analysis model working together. the the first one is gas collection model used to collect sense samples, but the volume is large and the energy is high. And the sensor array, the critical of current gas is realized through the combination of different sensors, but the structure is conclusion. And then is data analysis model. It is responses for species processing and pattern recognition, but it has a high requirement. Based on those problems, our design focus on solving the high weight and intelligent requirement. And then is part 3, our design object. Our proper electronic nose will avoid the following goals. The first one is portability through output significant layout and integration. And the second is intelligent, based on wireless transmission model, real-time data transmission to mobile phone. And part 3 is wide applicability. The equipment can be used in scenarios such as the human monitoring and so on. In summary, our design aims to provide the user with more convenient gas detection service.
Here's our design process. First, we select suitable circuit components based on the working principles of electronic nodes. Then, we choose the appropriate sensor according to the specific testing requirements, such as MQ3 sensors for alcohol detection. Next, we develop the code to control the circuit and ensure it operates as intended. Once both the hardware and software are ready, we conduct operational tests to confirm the system works correctly. Finally, we test the system with real samples to evaluate its performance and make any necessary improvements. In this circuit design project, we prepare alcohol samples, MQ3 sensors, and an Arduino microcontroller board. The Arduino microcontroller board complements this design perfectly. It is widely used in the prototyping due to its flexibility, easy of programming and compatibility with various sensors and modules. Additionally, Arduino's ability to seamlessly interface with computers allows us to write, upload, and execute code while retrieving real-time data from the sensors. The MQ3 Sensors module is a fully integrated circuit that includes a low resistor and signal amplifier. The sensor was chosen because of its high sensitivity to alcohol, making it particularly suitable for detecting alcohol samples in a wide range of concentrations. We construct an alcohol detection circuit by the Arduino board, LED lights, and two MQ3 sensors through a sample program written in the Arduino IDE. Both sensors were successfully operational. During testing, we observed difference in the performance of the two sensors. Sensor 1 exhibits a high baseline and tends to report higher measurements. After detecting alcohol, its readings were slow to return to baseline. Sensor 2 had a lower baseline, more stable readings, and faster response and recovery times. Based on these observations, we select Sensor 2 as the primary component, with Sensor 1 serving as a secondary sensor. We designed the following operational logic. The baseline output of Sensor 2 is calibrated to 0 via code. When Sensor 2's calibrate out exceeds 50, the green LED lights up, indicating the sensor is actively detecting. If Sensor 2's calibrated output exceeds 250, the red LED lights up, signaling an alcohol concentration beyond the normal threshold. For Sensor 1, when its actual output exceeds 250, the red LED flashes, indicating the system is not ready to work. We conduct testing using 70% alcohol samples. The sensors display real-time measurements data on the computer, and the LED lights functioned as pre-programming logic. The data phrase temperature during testing clearly, and the system's behavior across the three phases. At the start running, the sensor baseline remains stable as the system initializes. When exposed to alcohol samples, the output values rising rapidly, forming a parabolic curve that peaks at the highest concentration. In the running process, as the alcohol continues to change, the sensor readings slightly in a wave-like pattern due to the airflow variations. After running and removing the alcohol sample, the output value decays and quickly back to the baseline. These results confirm the readability and effectiveness of our electronic nodes in detecting alcohol vapors. Building on this success, we invention extending the design to create a portable electronic nodes for the daily health monitoring. The advanced design includes a gas collection with a replaceable single-use mouthpiece and gas filter, and a controllable one-way valve for safe and efficient gas collection. A sensor chamber with 6 high-sensitive MOS sensors configured as an array to detect various of VOC gases. A controlled model equipped with a wireless transmission unit to manage operation like an electronic pump to regulate gas flow and transmit real-time data to the user's device. We believe this portable electronic node has significant potential in household health monitoring and rapid diagnostic screening, offering a convenient and efficient tool for everyday health management.
Now here come to the existing problems of our design and the methods we provided to optimize it. The first problem is sensor selections and the performance of it. And we know different sensors show different performance due to aging or different batches of products. And for example, in our design, there are two MQ3 sensors, but they show the different baseline. And for these questions, we want to add an adaptive calibration algorithm to handle it. And now here's come to the second problems, that is the sensor array design. And we know the more sensors bring stronger detection ability for very small molecules, but more complexity at the same time. So it's a challenge for us, and so we want to use some modular sensors to try to solve these problems. And the final problem is the programming and equipment updates. Up to confirm that it's a big question for us when updating our equipment. So we want to develop an intelligence management application. Well, in the future, I think our design in noise can be used in many areas. It can be used in industrial park safety and production optimization. It can be used in air quality management in smart homes. It can also be used in agriculture environment monitoring and precision management. And above all, after the testing, we have confirmed that the products can correctly identify the alcohol concentration in the air. However, due to various factors, we were unable to integrate the 6 sensors into the same circuit. Our in-noise design is only a simpler version. We can only use it to detect the alcohol concentration. Even in our primary design, we want to test at least 6 kinds of the molecule in the air. But at least we have achieved the purpose of lightweight and portability. I think there's still a long way for us to improve our design, such as in the intelligent control, information transmission and stabilities, and most importantly is the number of the sensor we can handle. Thank you.